All right, Le Chatelier's principle is next up on the list. So Le Chatelier's principle deals with equilibrium and systems that are at equilibrium. So systems where, again, the products and reactants are made at the same rate. Okay, so it's a reversible reaction going back and forth. Le Chatelier's principle actually is based on predicting what will happen to equilibrium if a stress is added to a system. Now, what is a stress? A stress is changing the concentration, changing the temperature, changing pressure if it's a gas, all right? These are stresses. So if I have a container in which is at equilibrium and all of a sudden I add a stress to the container, it won't be at equilibrium anymore, and we say that it shifts. If we say it shifts to the right, we mean it shifts to the product side, because products are written on the right side of an equation. If we say it shifts to the left, that means it shifts to the reactant side, okay? And all that means is, when we say a shift, if it shifts to the product side, it means the rate at which the products are made speeds up, so you can start making a whole bunch more products, all right? If we say it shifts to the left, all right, where the reactants are, then that means that a whole bunch more reactants are going to be made. So it's not at equilibrium more. The rate at which you're making either the products or reactants will speed up. So we're going to look at these. All right, so once again, if a shift is applied to the system at equilibrium, it shifts in a direction that relieves that stress. So if we have a stress added, it's going to relieve that stress. And here's some examples of stresses: concentration, volume, which is pressure, and temperature. All right. Changes in concentration. So we're going to look at concentration first. All right. By either adding in or taking out, all right, some of your reactant or product, you will cause a stress in the system. This will cause the system to shift. So the equation we're going to look at, and again, as we're going along, I'm going pretty fast with these. You can pause to write this down if you'd like. So we're going to look at this equation right here. We're going to look at carbon monoxide gas plus hydrogen gas producing methane gas and water in gaseous form. Now, we can see it first. This is at equilibrium. So we're at equilibrium. We'll say this is in a container, a balloon, okay? Whatever, a beaker. And so this is happening. And then all of a sudden we're going to add a stress. So we're just going to look at concentration first. So let's look at the first one here. All right, our stress is we're going to add in more carbon monoxide. All right, when you add in concentration, what's going to happen is these now are going to collide more. Since these will collide more, when they collide, they'll make products. So when you add in concentration to one side, the equilibrium will shift to the other side. So we're going to make a big arrow there and a smaller one there. So we have a shift to the right. If I add more concentration, increase the concentration on the reactant side, it shifts to the products. Okay? Now you got to think of these reversible reactions. So these are colliding to make the reactants, these are colliding to make the products. They're going back and forth. Now what we're going to do is we're going to take out water. So we're decreasing the concentration of water. That means less of these are hitting together. So since this is equilibrium is about the rate, how much is being made, there's less of this being made. So small arrow that way, and still a big arrow that way. Okay, so what's happening is, if you decrease the concentration of one side, the equilibrium will shift that way. So this is a shift to the right. So I decrease my concentration of water, right, which is on the product side. I'm going to shift to the right towards the product side. I've got to make more of it. Okay? So, add in concentration to one side, it'll shift to the other. Take away concentration from one side, it shifts towards that side. So see if you can do these. You can pause it. I'll go along. So what's happening here is carbon monoxide is taken out. Which way is it going to shift? All right, I'm decreasing the concentration on this side, which means less of the product's going to be made. A lot more of the reactants. So if I take out carbon monoxide on the reactant side, it shifts left to make more of it. Next one here, I'm adding in water on the product side. Well, if I add in here, these are going to hit more. So I'm going to make more of my reactant. So this is going to shift left as well. So for this last one here, I add more concentration of water. Boom, I'm going to shift to the opposite side. Once again, if I take out decrease the concentration from one side, it shifts towards that side, in this case reactants. If I add more concentration to one side, it'll shift to the opposite. Add more water, in this case it's going to shift to the reactant side. Alright, changes in volume. Alright, volume is another stress on equilibrium, and volume and pressure related. We'll talk about that next chapter. And so what you're going to do, I'll read this, it's easier to explain as we get there. Changing the volume at equilibrium shifts the equilibrium only if the number of moles of gaseous reactants is different than the number of moles of gaseous product. When we deal with volume, we're only going to look at gases. Gases only. Right? Now, it's only going to cause a shift if there's a different number of moles of gaseous reactants and products. If there is a different number of gaseous products and reactants, right? If the moles are different, when the volume increases, there's a shift towards the side with the higher number of moles. If the volume decreases, there's a shift to the side with the smaller number of moles. Okay? So, here's what I mean. We're going to increase the volume. Okay, we're going to make the volume bigger. So, if you make the volume bigger, another way to say this is you lower the pressure. Okay, when you make the volume bigger, pressure goes down. So you're going to make the volume bigger. We're going to shift towards the side that has the higher number of moles of gas. How do you know how many moles they have? Well, we look at the coefficients here. Okay, so we have 1 for carbon monoxide, 3 for water, so we have a total of 4 moles of gas on this side. 1 methane, 1 water, so we have a total of 2 moles of gas on this side. So if we increase the volume here, make it bigger, it's going to go towards the side, shift towards the side with a larger number of moles. That's the reactant side for this one. Bigger arrow on the reactant side, smaller arrow towards the products. So increase the volume on this one, this is what will happen. Let's look at the opposite. Let's decrease the volume. When you decrease volume, that also means pressure is going up. When this occurs, it's going to favor the one that has the smaller number of moles of gaseous particles. 4 and 2 here. So if I decrease the volume, smaller size, it's going to shift to the side with the smaller number of particles, of gaseous particles, in this case to the right. So that's how volume and pressure work. Again, if I increase the volume, what I'm doing is decreasing the pressure. So if I decrease pressure, shifts to the side with a larger number of moles of gaseous particles. If I decrease the volume, meaning I'm increasing pressure, it's going to shift to the side with the shift to the side with the lower number of moles, Alright, changes in temperature. If you have an exothermic reaction, when the temperature is increased, there's a shift to the left. When the temperature decreases, there's a shift to the right. Okay, the exact opposite of that is true. If it's an endothermic reaction, when the temperature increases, it shifts right. When the temperature decreases, it shifts left. To show this, I'm going to write a reaction up here for us. So give me a second. If you have carbon monoxide plus hydrogen, right? This is the same one we've been doing. Gives our methane plus water plus heat or energy. So as I look at this reaction here, it's a reversible reaction. When I look at this, right, this is an exothermic reaction the way we wrote it, right? Heat's on the product side here. So if I increase the temperature, that means I'm sending energy in, okay? So if I increase the temperature, I send energy in. It's kind of like concentration. If energy goes in here, it's going to shift to the opposite side. Okay? If I all of a sudden made this colder, meaning I'm taking energy out, so I'm going to make this colder, so energy's coming out, then I'm going to shift towards the product side. Okay? So if I decrease my lovely temperature, I'm going to shift right here. If I increase my temperature, I shift left. This is an exothermic reaction, so that matches up. If it was endothermic, it's just the opposite. Alright, I really like Le Chatelier's principle because it helps explain some fun stuff. such as this. Let's say you're hiking, all right? Maybe you've been ever hiking or running in the mountains. We're talking about really tall mountains. You're going to see you get tired at a faster rate. Now, why do you get tired at a faster rate? Well, when you go up into the mountain, there's less atmosphere around you, which means there's less oxygen to breathe, okay? So at higher elevation, there are fewer oxygen molecules. Well, if we were to write down, all right, if we were to write down the equation for how oxygen works in your body, what you have in your blood is hemoglobin. All right, hemoglobin in your blood is what the oxygen attaches to and goes to your cells. All right, oxygenated hemoglobin is the only way your cells can get in oxygen. Okay, so it needs the oxygenated hemoglobin. So this is our reaction here. We've got regular hemoglobin, all right, with oxygen. When they get together, you make oxygenated hemoglobin. Okay, this is what your cells need, all right, for respiration. So to get that energy to hike or run up in the mountains. Well, since there is less oxygen at higher elevations, all right, since there's less oxygen at higher elevations, there's a shift to the right. Meaning, if we take out this concentration here, so we're decreasing this, okay, we're decreasing this, what's going to happen is we need to make more of it. All right, so the shift is going to be, all right, this should say left. I'm just now seeing that up here. Sorry about that. It should say left. So, if we take out oxygen, okay, if we take out oxygen, there's going to be a shift to the left here. Thus, what this means is there's less oxygenated hemoglobin for your body. So as you go in the higher elevations, there's a lower concentration of oxygen. Your body will, this process is a chemical process, so less oxygenated hemoglobin will be present. If that's not there, your muscles can't take it in and do the work. Now, people live in Colorado and stuff like that and actually get used to it. Right? Now, what does that mean to get used to it? Well, it doesn't mean they're tired all the time and they're okay with being tired all the time. What actually happens is they're not tired all the time. Well, how can I make this equation, all right, how can I make this shift back the other way? Well, here's what your body does. Your body starts making more of this. So it starts increasing, putting more, all right, hemoglobin into your system. Well, if I increase the concentration on one side, it will shift the equilibrium the opposite way. So what will happen to counteract the lack of oxygen, the body, if you live up in Colorado for a while or some other place at high elevation, the body will start making more hemoglobin, shifts the reaction towards the right, right? And there you have your oxygenated hemoglobin. So we'll get back to normal levels. So for those runners or bikers or something, here's a cool thing you can do, and here's what a lot of athletes do if they're getting ready to train for the Olympics or something like that. They'll go into the mountains, train in the mountains, okay? Get used to the lack of oxygen in there, so what happens is you have a whole bunch of oxygen, you get a whole bunch of hemoglobin, but you don't have a lot of oxygen. So your body starts making more and more hemoglobin. Then what they'll do is they'll come down, all right, from high elevation to do their competition. Well, what happens with that? Well, I have a high level of hemoglobin now because I've been in the mountains for a while, and now when I come down, I have a higher level of oxygen. What does this mean? It means you have a whole bunch of oxygenated hemoglobin, which means your body can go a lot farther, all right, because it's got a lot more oxygenated hemoglobin that's getting to your cells, allowing for more respiration to occur.